You said never let me go.
Hey guys, so in this video we are going to discuss about the Kepler's law of planetary motion, the third law of Kepler, and we are going to make an analysis on our solar system by calculating the time period, and we are going to plot a graph for that. And after that we are going to have a look at the Lagrange point for James Webb Telescope, and we are going to code it. The L2 and L1 Lagrange points we are going to code for that. Okay, so I think we should start now. So the Kepler's third law states that the time period square is directly proportional to the radius cube. So you can just get through the this theory part and you will know what is the Kepler's third law. Okay, so these are the predictions which are given. These are the predictions which are given by the Kepler's law, but we are going to make it on our own by using Python. Okay, so let's start coding. So first we are going to import some of the packages. First we are going to import maths, then matplotlib, numpy, scipy, sympy, and we are going to import constants from scipy and s2py. So this is the formula for you can say the Kepler, that t square equals to 4 pi square upon gm a cube, which is the this is the atmosphere, au the astronomical unit, r cube you can say. Okay, for this is defined for earth, and we are going to generalize it. So first we are going to define the mass, which is the mass of the earth. We have taken it in kilograms. Then the orbital parameters of the planets, so we are going to get it from this website. So you just have to copy and paste it. So I am going to copy this link, and will open a new folder so that you can see how we are going to collect the data from here. So it is taking, yeah. So we in Kepler's law we want first the mass and then the semi major axis. Okay, so here you can get the mass. You just have to copy all of this, the first column of each of this for each of the planets, and you can just copy and make an error for masses. And then the distance from the sun, which is, you have to keep in mind that it is 10 to the power 6 kilometers and the mass is 10 to the power 24 kgs. Okay, so if after getting these both quantities, we are going to construct an array. So here e denotes uh, tens. So it raised to the power, it says that 1 times raised to the power 10 times raised to the power 24, 10 times raised to the power 9. So okay, so we have defined mass with this array, and a with the semi a as the semi major axis. So these are corresponding values, that is the first term of this array will be is corresponding to the first term of this array. Okay, so you have to keep this in mind. Now we are going to define this formula in a Pythonic way so that Python could understand it. So we'll define it like this. So we have taken t only, so we have uh, taken the square root of this quantity. So after defining t, like 2 into math.py, we can also use uh, yeah, we can define it very easily. There are various different methods and packages to define pi and all, but it's good to define with maths because it is the most basic one. Then after that we are going to construct a table. For that table we have firstly defined the column, and then we have taken the value 1 and value 2, which are the test time period for test masses and two body system. So and we have taken the deviation also, which is d1 deviation, which is value 1 minus value 2. So after defining it to two decimal places, okay, we have taken time for two decimal places, and yeah, so after defining it in the format of this as given here, so we are going to get the time period for respective as we have defined it with respect to us. So we get that one for time period for earth, that it signifies 365.25 days for earth, and if you are going to multiply 365.25 with corresponding t value, you are going to get the number of days which are equivalent to Earth days. Okay, so yeah, so after that we are going to make a plot for this. So here we have taken the log plot, because log will make a linear graph, and to define it linearly we have to take this log graph. So we have just simply x label, y label, and given square boxes, blue square boxes, so it forms a linear combination with we have a time period, and in year time orbital period in years, with the semi major axis and the as x axis, and orbital period as y axis. So I think you get the theory part as well as the coding part for the Kepler's theorem, Kepler's third law of motion. It is simple, and if you have any doubt regarding this, you can comment down below. And if you want to make some changes, like you want to take, you want to talk about the Earth and Moon system, Earth and the Jupiter Moon system, and all, so you can easily define it in this array. You can change it in this array, the m and a values. Rest other will stay same, so you can get the answer easily. Okay, and yeah, so after that we are going to apply this to our James Webb Telescope. So James Webb Telescope is recently parked in the L2 orbit. L2 is a special orbit, and these all the 5 points here mentioned are called Lagrange points, in which the special thing about the Lagrange point is that they have a orbital period same as that of the Earth. Okay, so it is just like having in a geostationary orbit, the satellite in a geostationary orbit, but in this case we are having a satellite which is orbiting the sun with the same orbital period as of Earth. Okay, so these are very special points, and in this video we are going to calculate L1 and L2. Okay, yeah, and James Webb is in L2 orbit because it wants it the scientists do not want it to expose to the solar radiation directly, and that is the reason it is behind Earth. Okay, yeah, so yeah, this is the definition for Lagrange points. And okay, so first we are going to define the constant here. First we have the mass of sun, then mass of Earth, and the radius, which is the distance from Earth to sun. Taken a mode argument also, which gives only positive values. Okay, so this math.fab is a modulus function. Okay, as we know that distance cannot be negative, so we are taking it as a precaution for this. So let's calculate the L2 orbit. First we are going to define FD, like yeah, let me just take you to the formula that how we can derive this. Okay, so this is the, I can say, a sketch for the following how we can derive the formula. So we have taken a three body system in which sun, earth, and a satellite is there. So earth is revolving around sun, and a satellite is also revolving around the sun with the velocity v1 and v2 respectively. So after that we can say we have taken an assumption of that mass of sun is far more greater than mass of earth, and mass of earth is far more greater than the satellite. So in this step 1 we are going to balance forces for sun and earth. So here we have taken the centripetal force and the gravity force, with for the centripetal force, mass into velocity square upon radius equals to g m1 m2 upon r square, Newton's law, and simple centripetal formula. After defining it, we get to this point. Oh yeah, so we are going to solve it for v1. So after solving this equation for v1, we are going to get the value of v1 as root gms upon r1, which is the orbital velocity of our earth around the sun. In the step 2 we are going to take a 3 body system in which sun, earth and satellite will be there, and we are going to balance the forces on it. So centripetal force acting on the satellite and the gravity forces acting on the satellite. So here you can see the gravity forces on the satellite is both due to earth and sun, and it is in the same direction. But in case of L1, the force for the earth, force of gravity will be different, so keep that in mind. Okay, so after solving, we get this expression after putting the values and all. So the special thing about Lagrange point is the angular velocity of earth and satellite are same. Okay, the orbital velocity is same, that is the time taken by the earth to revolve around the sun is same as that of the time taken by the satellite to revolve around the sun, that is 365.25 days. Okay, so so we can say that we are equating the angular velocities for both of the orbits. So v1 upon r1 will be equals to v2 upon r1 plus d, which is at an extra distance d, the satellite at an extra distance d. Okay, so we have taken it into account here. So after putting the value of v1 in this equation, we get the value of v2 as r1 plus d divided by r1 and root gms divided by r1. So we are going to put the value of v2 in this equation, in the second equation. So after putting all of this, we are going to get this equation, and to simplify it, we have multiplied it with r1 plus d square into r1 plus d whole square into d square. So after multiplying, we get this simplified equation, which we are going to define in Pythonic way. This equation is for the L2 orbit, and for the L3, for the L1, for the L1, we are going to repeat the same process, but we have to take in account the gravitational force for between earth and the satellite is in the negative direction. It is going to subtract, where in the earlier case it is adding. So solving it in the similar fashion, we are going to get this equation, which is for the L1 orbit. Okay, so let's get back to our Jupyter notebook to code this. So we are going to define our function which with d as a variable, and we are defined the L2, that is this equation in the Pythonic way, and we have taken a differentiation f with respect to uh, differentiation of f with respect to d, then differentiation of f, double differentiation of f with respect to d, as we have done in class 11 and 12th. We are going to do it by that only. Okay, this is easy stuff. So after that, we are going to, why we are taking the differentiation, so we are going to use the Newton-Raphson method. This is the quickest method to get our values. So if you want to know about Newton-Raphson method, you can refer to the YouTube and search for the videos in questions, and you will get to know about that. It is easy stuff. Okay, so after defining it, we are going to define another function which is going to give us it is a loop, it is a while loop, and it is going to take different values, give different values, and it is going to give the answer as a root, which is going to be our L2 orbit, radius from the earth, radius from the sun. So after printing Raphson method and taking 1000 as the value, that it is going to supply the input and 1000 time until it get the root. So in the first analysis, we get 1.5 million kilometers for the L2, and doing the same operation and defining the L1 equation here, doing the same operation all around, not changing anything here in this, just changing it to minus, I guess. A minute sign difference is there only. Okay, rest other code is same. So in the second case, which is the for the L2, we are going to get the orbit as this. So I think let's check it that we are correct or not. L1 L1 orbit, okay, radius. So L1 orbit radius, it is given 1.5 million kilometers, and same, it is not precise it is given on Google, but we have taken a precise value and find it. Okay, and let's see about the L2 now. So L2 is again 1.46. Yeah, no, this no L2. Yeah, it is also 1.5 10 to the power 6 kilometers. Okay, so we can say that we have got a very good precise answer. And for other points, for L3, L4 and L5, we are going to continue the series, and in the coming future we might do this. And if you want me to make a separate video for all of the other 3 points, do comment down below, and keep subscribed to the channel. In the other video, in the next video, we are going to talk about the asteroids, as we have taken a base tour through the Kepler's law. We are going to be comfortable with the asteroid as well. Okay, and you can just get this code from the GitHub site. So you can go to the YouTube Coding My Universe. You are going to land on this page, Suruf Kumar PHY Physics, and you have to go to the repositories, open it, and then YouTube Coding My Universe, open this folder. Then you are going to find this video 2 code, and if you want to commit any changes and all, you can do it on your own device. And if you allow me, I can show you something else, that we are going to here discuss about beam optics, the Campton scattering, and classical physics problem, spectral analysis. A lot much is coming in this on this channel, so stay tuned to it. Okay, ask your friends to make these projects, and you are going to love it. Okay, and surely my college journey is going to begin. I am going to post
You
some vlogs.
said